But we can create an alternate load path by the vertical component of the external post-tensioning actually diverting past the critical failure plane that you're worried about and going directly to a column or wall support. Previous versions of ACI 318 had a specific section dedicated to this, but with the redesign of ACI 318.14, you'll see kind of scattered discussions about external post-tensioning, but that's largely because it's well accepted now. Typically, we're going to want to involve a specialized contractor. This is not the type of repair that you want to go in, produce a set of drawings, and have a low bid contractor or engineer who's not familiar with this come and try to do this. We're dealing with very large forces. They are outside of the building itself, and it takes a lot of expertise and care to do this correctly. Well, when do you consider external post-tensioning? When you have damage due to corrosion and exposure to salt water, snow, de-icing salts, other chemicals, being close to the ocean or being up in the mountains has been where corrosion accelerates. And it's largely due to somehow getting salt, water, and air mixed with metal. There may be additional load not accounted for in the original design. That has happened to us. Landscapers come along and add a lot of landscaping load. Soil can be some of the most heavy load that you'll ever apply to a building. A change of occupancy. The architect may want to change the occupancy of the structure, so the live load changes. Topping slabs, landscaping. So first, if we're talking about corrosion, what are the signs that you've lost strength due to corrosion? Well, concrete is a wonderful material in that it expresses itself well. It communicates to you. If you will listen to the concrete, it will talk to you. Unlike my wife, which I have difficulty sometimes communicating with, concrete will tell you exactly what's happening. This particular concrete said, I am suffering, and it shed a large chunk of concrete. This is actually lightweight concrete, and we're talking about structures now. The structures that are starting to disintegrate were built in the 70s and 80s. So we're seeing signs of that, the 30, 40, 45-year-old buildings. This is from up above that. So the concrete is saying, hey, something is wrong with me, and I'm going to show you what it is. Now, what you're looking at back in the 70s, the really popular way of external or of post-tensioning was to wrap it in paper. They weren't thinking about the extruded plastic that we have today. They weren't thinking about long-term corrosion. What they were thinking about, post-tensioning was relatively new in the 60s and 70s, at least in the United States. And so they wrapped it in paper, greased it, and the post-tensioning pre-stressing steel needed to move while it got stressed. After that, they weren't thinking long-term about it. And what happened was the paper, if exposed to water and the lightweight concrete, the paper would start to corrode, the water would get in, and the process of corrosion began happening. And over 20, 30 years, the steel starts to disintegrate. Now, this is post-tensioning being moved by your finger. Now, if you've ever actually touched stress post-tensioning, which I have because we do a lot of external post-tensioning, you can't move or budge that steel. But if you can move it with your finger, if you can move it with a screwdriver, if you can move it with anything, then it's not stressed. And that's how you know. This is one of the more dramatic things right here in Newport Beach that we got called out to. This was the slab up above. I'm taking a picture looking up, again, at paper-wrapped tendons. This is what you can expect to see if the building was built in the 1970s. It's not plastic, it's wrapped in paper. This is about as dramatic as it gets. That up above, I hope you can see my cursor, was what I was showing you in the previous picture. This concrete fell right onto this car, went right through the sun roof, and landed in the child's seat. So it doesn't get much more dramatic than that, of telling an owner that, hey, you have a really serious problem that you need to address. When the concrete starts landing in the child's seat, people will take notice. Other signs of corrosion look like this. The tendons will start popping. What you will notice first is concrete staining. That's the concrete speaking to you. It's saying, hey, something's not right. I've got corrosion byproduct leaking through me. I'm exposing it. I've got a large crack. Just look at me. A few years later, that will look like this. Now, this is just rebar. This isn't a post-tension structure, but it doesn't matter. We fix and repair and find the same corrosion problems in reinforced concrete. By the way, that Surfside condominium project in Florida that collapsed, that I think everybody in the world knows about, was just a reinforced concrete slab. It was not post-tension. But, you know, I don't know what happened there, but we're seeing reports that they had damage that looked like this. A post-tension structure will talk to you also. It will, when post-tensioning strands fail or rupture for some reason, they'll poke out of the building, say hi to you, say, hey, look at me, something is wrong, Mr. or Mrs. Engineer, you need to address this. This is the same structure from below, but the post-tensioning tendons will just pop the grout pocket, shoot it out, and come out of the building. But again, concrete is great at expressing itself to you. So it's showing you that something is wrong. Be very careful when you're called out to look at a 40-year-old building. Walk every square foot of it. Walk the top of the slab, walk the bottom of the slab, walk all the side edges and see if the concrete's trying to tell you something. This is a very common type of failure of post-tensioning. This is a later type of post-tensioning. It's got the extruded plastic around it. For one reason or another, when a concrete stressed strand fails, it releases that energy and snaps, and it will find the path of least resistance, which is where the cover of the concrete is the least, and pop out. Now, the interesting thing is that the breaking point of this particular strand, and usually the case, is nowhere near where the tendon pops out. This just happens to be where it could get out of the structure. The severing or the failure could easily be 100 feet away in this particular strand. I found this picture to be somewhat funny. We were called out, and it's interesting how owners and property managers think that as soon as they see something, it must have just happened. And they tried to tell us that these tendons just came out of the concrete within the last week or so. And I asked them when they last painted the stalls, and they said that was a few years ago. So clearly that didn't happen within the last week. The tendons may pop out of the bottom. Again, they're going to usually find the location where there is the least amount of cover. The path of least resistance will be where the tendons come out, but you may have to follow that tendon line for 50 feet or 100 feet. Okay, I'm not sure what happened. It said the host muted me, so I hope you can hear me. I believe I'm unmuted now.
Yes, I can hear you, Mr. Bondy.
Okay, very good. Okay, I will keep going. So the tendons come out at the path of least resistance. This was an interesting project in that we were called out to look at this, and I don't think I'd ever seen this before, but the tendons were actually popping out of the side of a beam. Now that's highly unusual because the tendons are usually towards the middle of a beam and within the stirrups, but for some reason, this tendon actually decided to pop out the side. So like I said, it'll find the path of least resistance. Now, this is an interesting structure, particularly given the Surfside situation. This was a building, a hotel, it's changed names, in San Francisco. We did this in 2003, so this was 18 years ago. But not unlike the Surfside condominiums, where there is a tower portion and a slab that extends out one level well beyond that tower portion, but also goes back underneath. So they're connected. Again, there were signs that the concrete had kind of been thinning on top and whatever exposed rebar was starting to make its way out. This I can't emphasize enough. If you take nothing away from this talk other than this, you will have succeeded in learning something valuable. In this particular hotel, this was 2003, they had lost post-tensioning, and we externally post-tensioned the deck below this holiday. It was a Holiday Inn at the time. It's something else now. But we got concerned about punching shear. I am always concerned about punching shear. These slabs may fail in flexure, but flexure is a very, it's the safest type of failure that you can have. You can see it coming. There's a lot of upfront information telling you that something's wrong. The slab may deflect a foot or 2 feet. It usually is not what's going to create a pancake type collapse where one level collapses onto another and collapses onto another. What causes that is a punching shear failure. And again, I'm not aware of exactly what happened at the Surfside in Florida, but most of us believe that one reason or another, the failure led to a punching shear failure, and it was that punching shear failure that led to the collapse of the building. Now, I don't know that to be the case, but it's almost always the case with a flat plate that punching shear is what causes the major collapse. So we didn't skimp. We went in and put in these beefy angles to increase punching shear along with the external post-tensioning. And if I had to pick one of the two to do on this building, if I could only do one, we would have done the punching shear because, like I said, failure in flexure, you can see coming. It's not as dangerous. It's not fun, but it's slower. It shows itself. Punching shear doesn't show itself till the immediate collapse happens. You get no warning on that. That's the one to be scared of, and that's the one you should always strengthen for, even if you think you have enough capacity. Now, this particular failure, my father was called in to look at this. This was 1994 at the Northridge earthquake. This was not corrosion, but you get the same effect. This is still a failure. This was a failure during an earthquake of a connection to a concrete shear wall, the deck connection to the shear wall. By the way, I hope none of you use those delayed connections where you allow a temporary release and slipping of a slab along a seismic system and ask the contractor to come back in later and connect it, because they don't sometimes. And in this particular case, they didn't. And this led to a failure. We never use the temporary releases. We find other ways to do it. That's a different talk. But I want to show you, this is what punching shear failure looks like. Now, however it starts, it's usually the failure of something like the connection to the wall. One area fails, and then that overloads a column. That column fails in punching shear, and the domino effect is the building unzips. It unzips until the entire thing collapses or until it breaks along a slab line. Now, what you're looking at here, that is a column right there that has punched up about 3 or 4 feet through the slab. The slab was up at this level. That's my father walking up the slab that used to be flat the day before. But this is what punching shear looks like. Now, we have this wasn't our building. We were called to look at it. But they got very lucky because the slab actually failed in flexure along this line, which turned out to be a great thing. You actually want that flexural failure. Had that not happened, there's a good chance this would have continued to unzip and continued to have punching shear until the entire building came down. So you're evaluating corrosion and paper-wrapped post-tension systems. If you see through cracks, if you can see daylight from the bottom, there really, by definition, is no pre-compression in the slab. Doesn't necessarily mean there's nothing in the tendon, but it means there's nothing in the slab, and there's probably nothing in the tendons. If the through crack exists where you have a location of high bending and it's not a restraint type of crack, chances are that's the concrete telling you that it's lost most of the pre-stress that was in the system. Here's a very common mistake that I hope nobody listening does. Most engineers will decide in a post-tension building, if they think there's been a corrosion problem, to expose a piece of the pre-stressing, either at the end, somewhere in the middle, chip out an area and stress the tendon there, or go to a pore strip, somewhere that they can put a jack on and do what's called a lift off, or try to stress the jack to see if there is tension in the tendons. The problem with this is if the tendon has corroded and it has failed, or it has no more pre-stress in it, that corrosion byproduct will still, it actually grows on the tendon. It will actually grow and bond to the concrete, even though it wasn't originally bonded. It will bond to the concrete, and then it creates a serious bond friction. So you apply a jack to that, you will actually get high jack forces. And I'm sorry, I can hear somebody talking through there. If you get those high jacking forces, you may misinterpret that, and many engineers do, as saying, well, there's still plenty of pre-stress in those tendons. And you could actually be checking a tendon that has been broken somewhere. So a lift-off test is probably the worst way to try to determine if you have lost pre-stress. The best ways are simply getting in there with a screwdriver and trying to move, or one of those car jacks, trying to just see if you can move the tendons. That to us is the best indicator of whether or not there is pre-stress in the tendons. So you need to look at all of the evidence. Don't focus on anything like one particular liftoff test giving you all the evidence. You've got to take the whole building forensically into account. Distinguish between the different types of cracks that you're looking at. Post-tension buildings, especially the older ones, will have restraint cracking in them. That restraint wasn't as well understood in the 70s and 80s. So it's not unusual to see restraint cracks. Those don't mean that you've lost post-tensioning. You really have to try to look and see if that crack is telling you it's in a flexural zone, or if it's just restraint and in a corner. And I said, and I keep saying, that just trying to evaluate locally the strand itself may not give you a good conclusion. You could be looking at a section where the strand looks terrific, and 50 feet away, it's corroded and broken. So you've identified that you have a problem. Now what do? We start with repairing the concrete. We're removing all the loose concrete. We clean, we sandblast, all the corroded reinforcement. You're trying to arrest the corrosion from continuing. Replace, if you can replace the rebar, it's not that easy, but repair it, clean it. patch the concrete spalls, inject the cracks, try to seal the top of the slab if you can. Most of the time, the water and the salt is coming from the top. So coating with an elastomeric coating is very effective. This is what repaired concrete on our project has looked like. It's not particularly pretty, but the moisture intrusion and the cracks have been arrested. This is one of those large sections that had fallen from the slab soffit. Again, not particularly pretty, but Seneca, at least in the United States, provides very good products that can be used for repairing and patching concrete. Very high density, tight concrete, high strength. That's what you want. You don't want even air getting in. So now you've repaired the concrete, but what about the lost reinforcement? And that's the big question. You have to determine, have you lost enough reinforcement that you need to apply more reinforcement? And that's where the external post-tensioning comes in. Concrete's now been repaired, so you feel good about it. Hopefully you've sealed the top of the deck, so corrosion has been arrested, but you have to decide, do you have enough strength? It's very delicate because if you're fixing a post-tension building with post-tensioning, you've got to be careful not to make the problem worse. So you need to locate where you have strands and rebar. Get somebody who knows what they're doing to core the system. Sometimes the cores are small, sometimes the cores are large. Now we're always in a catch-22 situation where we're trying not to damage the building too much by repairing it, but locating where the existing rebar is and doing your best to core without losing strength on the element that you're coring is important. King posts, this has got intumescent paint for corrosion, fireproofing, is important. These are what divert the tendons and actually create the balance load point loads. Sometimes they're small like they were in the previous picture. Sometimes we have the depth where we can really significantly create large balance loads, push up on the slab without a tremendous amount of force in the post-tensioning. If you've taken a post-tensioning class, you know that that drape is what you're looking for when you're trying to create an upward balance force. So this was a project out in Palm Springs where a lot of extra load had been added to the slab up above. So the tendons end up getting stressed. Now I kind of apologize for this. This was back in, I think, 2004, 2005, early days of the iPhone. Go. But that's the stressing of a tendon. First, the slack is taken out. Then the tendon is literally stretched to get the force into it. Hard to see, but the slab is actually slightly lifting there. We could tell that the shoring was loosening as we were going through this process. I asked the guy doing this to turn the jack toward us. That's the hydraulic jack first taking out the slack and then literally stretching the tendon to get the force into it. Now, sometimes in this particular case, we were up in the mountains and we were subterranean, and you have to get creative when you do these things. We had to stress internally because we had no access from the outside of the building. They were underground. So in this particular case, we had to come up with an internal stressing situation where we would stress two tendons in this direction, move the jack over to the other side, stress the two tendons in the other direction, and just keep walking our way back and forth to get the force into the tendons. That's what it looked like from below. So creativity is your best friend. And they say engineers aren't creative, but if you're going to do external post-tensioning, you have to become creative. No two projects have ever been the same for us. We always have to manage some type of issue on each one of them. In this particular case up in the mountains, they had put so much de-icing salt on the top because of the snow that it had eaten away the post-tensioning in the slabs up above. So we replaced that post-tensioning for this particular slab, but then we applied a new slab up above, and we actually designed that post-tensioning slab to span beam to beam, and we overbalanced it so it literally was lifting up off of the slab below. So we balanced about 115, 120%. That slab was literally arching up above. So we're trying to keep it from loading the slab that's already had problems. But even during live load, they may touch each other. And so we have strengthened that slab from below, waterproofed it, done our best to keep that slab from further deteriorating, and then provided another slab on top. But that cumulative weight built up on these girders, and we had to do some pretty serious angled coring through these large columns to get that post-tensioning through. This has been standing there for about 16 or 17 years, so we're pretty sure it worked. But those were large chunks of, those are large forces in large cored holes and cored at an angle. So like I said, this is where a really good qualified contractor comes into play. Coring at an angle is not easy. They can all core flat. They can all attach their coring machines flat and perpendicular to something, but to get somebody to core at an angle isn't easy. So one-way slabs. This was a job actually in Newport Beach, not too far from here. This was our final product for fixing a slab only. I'll back up. It turned out that they didn't do a good job of sealing the top deck, which they promised they would. And we had to come back about 6 or 7 years later and apply a new slab up above, and then strengthen the beams and strengthen the girders too. So this is the project out in Palm Desert, two-way post-tensioning. This particular job, we decided to go at an angle and use 2 pickup points to lift this slab. Two-way slabs are by far the most demanding for creativity, is you've got to figure out how to get out to the middle of a slab bay and then get that load back to a column. So this was a diagonal method. And this is how we had to get through the column caps. Notice everything is galvanized. The tendons are galvanized. We galvanize all the hardware. We don't want to create another problem that in 10 or 15 years has a corrosion problem itself. And you'll notice we can't help ourselves. We're always strengthening the punching shear. That to me terrifies me. After 1994 and walking that job with my father, I'm terrified of punching shear failures on anything that I work on, so we're always strengthening that. This was a project in Anaheim that instead of going diagonally column to column, we went orthogonally. Now these are fun as a mind game to try to follow the load. This particular king post is the one pushing up in the middle of the bay. So we're out in the middle of the bay. That load is coming down the drive aisle. This is actually pushing down, not up. This is pushing down. It's pushing down onto these orthogonal tendons, and those tendons get the load to the column. So it is a fun mind game to walk through this and try to figure out how the load is getting from the slabs to the columns. This is a particularly aggressive external post-tensioning job that my father did. This was a case where it was about a 12-story building in Los Angeles. There was no headroom in any of the floors up above, but there was plenty of headroom in the lobby area at the first level. So all of the jacking happened in that lobby level, and above these were 12-story columns running all the way through the building. And the theory is dropping off equally, lifting each floor 1/12 of the load. It seemed to work, and it's still standing to this day. One interesting thing, there's many interesting things, but one of them is that not only are we a weightless system that's providing plenty of strength, but you can actually thread this through the existing mechanical, electrical, plumbing system. Most strengthening systems have to remove all of the other systems in the building, the duct work, the piping. That stuff all has to come down so that the strengthening can go in, and then all that system goes back in afterwards. We've actually been successful at just putting the external post-tensioning in and diverting around the existing system. Again, creativity is what this is about. This one scares me. This was my project. We did this a long time ago. I think we must have needed some work, but this was a wood warehouse, just a panelized roof system, and they wanted to put a cooler up on top of the roof, something on the order of 15,000 pounds or 20,000 pounds. And we decided to externally post tension so that they could do that. My distinct recollection on this project was that when they, these guys had never done this before. It's hard to find a wood person who's got experience, or anybody. But when they stressed these tendons, it lifted the glulam beams, and they started making a creaking and cracking noise, and everybody ran out of the building. They were absolutely terrified. But when it didn't come down, they went back in and decided it was safe, and they ended up putting that cooler on the roof. And it, again, to this day, is still standing. That was probably 2005, 2006. I don't think I would do this again, though. That's another view of it. But a couple of tendons was putting a pretty large upward balance force on those glulam beams. So how do you design it? What are the things you have to think about to design the external post-tensioning? Another common mistake for engineers who don't think about this as much as I have is that they go to the concrete stress portion of the code and try to satisfy that. You have to realize that these structures are terribly cracked by the time we get involved with them. But when somebody calls us out, the concrete's usually falling. There is absolutely no reason whatsoever to follow the concrete 6 square root F prime C, 7.5 square root F prime C, or anything. So that you just ignore. What you're doing is providing strength, and that has to be a discussion. The codes are very good at addressing new construction. They're pretty good at addressing renovations. They're really not at all meant for fixing and repairing buildings. So that's good and bad. I mean, that's mostly good, because that means that you get to sit down with the owner and the building department and discuss what makes sense and say, look, we're going to fix this building. We can't make it brand new. We're never going to, but we're going to dramatically improve it. While we may not be satisfying all of the code requirements, maybe not the fire requirements, maybe not some of the others, but the choice is to do nothing or to significantly improve the building. So that's a discussion I end up having all the time. Now, we can recover deflections, but never ever promise a flat floor due to external post-tensioning. Never understand the properties well enough of a severely cracked system to know how it's going to react. You can promise some recovery of deflections, but then if you need a level floor, use leveling material, use lightweight gypcrete, something like that, fluid flowing that can give the architect, the owner, the tenants a flat floor. But never promise that external post, it'll do magical things, but it won't create a flat floor. You're really talking about strength design, and you're going to get back some deflections. And that's what we're doing with external post-tensioning. But the strength part, you have to pay serious attention to. The code strength section still applies, and all the statics and rules of post-tensioning still apply. The code says, and whether or not the code says it or not, you have secondary effects that apply to post-tensioning. We use a load factor of 1.0 on those. Secondary effects are not well understood, but they need to be for strength design. You have to account for the secondary moments that you're imparting by stressing. Make sure to use software that includes that, because if you're just trying to hand calculate, you can miss these things. Remember, most of your post-tension buildings, all, the post-tensioning is actually in the concrete system. So your final pre-stressing forces from your balance loads and is subtracted from the primary pre-stress moments, F times E, give you the secondary moments, if you recall your pre-stressed concrete class. The primary pre-stress F times E is substantial when we come in below the structure. So you really have to understand and make sure you're accounting for correctly secondary moments as you are externally post-tensioning a structure. The protection of the external post-tensioning. Now that's definitely going to apply and something you need to focus on. They need to be protected from corrosion. The best way to do that is to use galvanized tendons, galvanized hardware, galvanized everything. We still grease it, which also gives it a level of protection, and wrap it in tightly as if it's an encapsulated type system in sheathing. We're doing everything we can to protect it, but the galvanizing probably does the most. The difficult, touchy part of this is the fire protection. Now, ACI 318 has a very interesting section. It says corrosion protection methods should meet the fire protection requirements of the General Building Code unless the installation of external post-tensioning is to only improve serviceability. Now, that's a touchy and interesting statement to make, because you're always getting some strength out of the post-tensioning, but you're reclaiming some deflection too. Now, the discussion that we end up making is that the building didn't collapse prior, and sometimes we make this argument. So we try to argue that the external post-tensioning, if we're comfortable with this argument, is a secondary strengthening method, that we're getting a strengthening benefit, but we're also recovering some of that deflection and now allowing a leveling material. If you can successfully make that argument and you're comfortable with it, then you don't need to provide fire protection. And the reason I bring this up is the fire protection can end up being more costly and time consuming than the external post-tensioning itself. So that's a delicate thing you have to think about. And I've sat with building departments and said, look, we'd love to fireproof the whole thing. It's going to be so cost prohibitive that the owner now won't do anything. And we want to strengthen this structure. So what do you think? You will always apply corrosion protection, by the way. So let's look at what this looks like. I think I've got about 3 minutes left if I'm staying true to 45 minutes. We galvanized the anchors, the caps, the plates, the tendons. This was an interesting discussion. This was a project, again, in Newport Beach, where we had repaired all the concrete, theoretically had sealed the top. It was going to cost much more to go along and fireproof every one of those tendons than the external post-tensioning costs. So we discussed with the building department adding a sprinkler system. The structure didn't have a sprinkler system before. It does now, and they agreed to that. So that's one of those situations where you've got to sit down, be confident in what you're doing, and offer a different solution. Now, this technically probably doesn't satisfy the fireproofing requirements, but everybody horse traded and got what they wanted in a strengthened structure. So, and most of the strengthening is voluntary. You have to understand there's very few things that will mandate that the building be fixed. Most strengthening is always voluntary. So we start with that, and we even put that on our drawings, voluntary strengthening. So kind of leads you to believe you can do whatever you like, but building departments don't always see it that way. This is what, when you do need to fireproof, this is what it can look like. This was a nice clean fireproofing of tendons and a king post. This is not very pretty. This was literally chicken wire wrapped. We use the section of the code that's for trusses. So the bottom cord of a truss, the way it gets fireproofed is the same way the post tensioning gets fireproofed, with the same amount of vermiculite or concrete cover on the tendons, depending on the hours required for the fire rating. I think I'm going to hit my time just right. I want to talk about load testing. Now, you're fixing a structure. You think you understand the structure. You may or may not have good drawings about the structure, and you're making a leap of faith that the building was built according to the drawings that you have, and that you have somehow identified all of the loss and corrosion and strength loss. You probably haven't. So we're doing our best guess. We're engineers. We're making good engineering judgments. But when you're going back to a 1970s building, it's a risk. One thing you can do and should consider doing is when you're done with all the strengthening, the concrete repair, the sealing, the external post tensioning, is to ask for a load test. Ask the contractor to provide a load test, perform one. United States dollars runs about $20,000 for a testing company to run a load test. It will test the strength. It's actually a deflection test also. But once you have passed a load test, it now no longer matters if you understand the structure, the way it was built. If you got it all wrong, it doesn't matter. If it passes a load test, the building code says it is a viable, strong enough structure. End of story, period. So if there's any doubt, if you want to cover yourself in liability, or just give yourself peace of mind and sleep at night, when you're done with this, get a load test, apply a load test, and sleep well. Eliminate all the doubt that what you've done